Hi guys. So I am going to attempt to do an equilibrium problem here, and I will say that I don't have a whole lot of time, so hopefully I don't flub this up too bad because unfortunately what you see is what you're going to get. So I pulled this one from another textbook. So this is from College Physics, 5th edition by Batista, on page 294 of that text. It's of course important to cite our sources when we use sources outside of the material that we've created. So what does this say? We've got basically a signpost, kind of a horizontal signpost that we're hanging a sign from. We're given the dimensions of the signpost, and we're given the fact that it's 1 meter long. The sign's going to be hung from a cord that's attached to the end of the signpost at that 1 meter. We are given that there is a cord that is supporting the signpost that's attached at a 30-degree angle and then affixed to the wall. Let's see, what else are we given? We're given the weight of the signpost. It says that the signpost has a weight of 198 newtons. Whoops. 198 newtons. There we go. How do I know this? Well, it says that the beam, the signpost, has a mass of 20 kilograms. Its weight's 198 newtons. Let's see, what else are we given? It says that this cord here can sustain a maximum tension of 920 newtons. And our end goal is to figure out what's the maximum weight our sign can have. Or another way of saying this is, how high could I make the tension in that particular cord right there before this particular cord right here actually snaps? So how much weight can I hang from cord number 2? All right, so here are our goals. Now, our first step on this is to draw an extended free body diagram. So we're going to draw an extended free body diagram of that horizontal signpost. That's our goal. That's the idea anyway. So something like, there we go. There's our horizontal signpost. And then we have to think about the different forces that would be acting on this. So we could have, say, let's see, definitely a downwards force there. Well, that's a really big arrow due to that cord that's that sign is hanging from. What else? We have, let's see, our cord that's suspending the signpost from the wall. Okay, I've done a bad job of drawing that angle there, but we've got that nice picture from the textbook that can help us out some to overcome that difficulty that I've introduced. What else would we have? Well, let's see. We would definitely have the weight of the sign itself. And I don't know how big those arrows are supposed to be, how big those vectors are supposed to be in relation to each other. So I've just drawn them some random size. Let's see, what else? Well, we've got this right there, that connection between the signpost and the wall. And so that the wall is going to exert some forces on the signpost as well. And looking at the direction that T1 is pointed in, it's kind of pointed to the left and up. So to the left and up. So I'm guessing that maybe my wall has got exerted force to the right to balance out that force to the left from T1. We'll call that H for horizontal. And then let's see, there probably is going to be an up or down force as well at the wall, a vertical force. And I might make the guess, and it's just a guess here, that maybe my vertical force would be upwards there to kind of help support the signpost. All right. There is my free body diagram. And let's see. My extended free body diagram. Now, the next step here is to, I don't know, maybe check off the things that we have. We definitely have T1. We definitely have the weight of the sign. T1 is, gets as large as 920, and the weight of the sign gets us, or the weight of the signpost is, is 198 newtons. We don't have either the horizontal or vertical components of the interaction of the wall with that horizontal signpost. And we don't have T2. Of course, our main goal here, as stated in the problem, is to get that right there. I have no idea why my line width has gotten so large in my drawing here. So that's very interesting. Oh, I see. I clicked the wrong button. Okay. Now that I've got that figured out, and now that we've got the kind of things checked off that we know and we don't know, let's work towards getting to our end goal, which is figuring out how big can I make T2? How much mass can I suspend from the end of this cord that's on the very end of the sign, or on the very end of this this beam. All right, so our main tool to do this is the idea that our torques have to sum to zero in order for this signpost to be in equilibrium, to be steady. Its net torque acting on it has to be zero. In order to calculate torque, I have to figure out the axis of rotation that I'm calculating torque from. Now, this idea is the same as maybe in earlier physics problems when we dealt with forces, and we said that we needed to define our X and Y directions. Okay. Well, just like we had to define X and Y directions before, now instead, we have to define our axis of rotation. Okay. All right. So the most convenient axis of rotation here, if I want to figure out something about T2, I definitely don't want to put my axis of rotation there. Instead, let's put it right there at the wall where I've got the largest number of unknown forces acting. All right. So my axis of rotation is right here. There's my axis. And any force that acts right at my axis of rotation is going to result in no torque from that force. It's like pushing on the door hinge of a door. If we truly push just on the hinge of the door, we're not going to cause the door to rotate at all. Same idea here. If the circled connection between the wall and the signpost there is our axis of rotation, then the forces that act at that point aren't going to cause any kind of rotation on that beam. All right, so let's work our way to the right from that axis of rotation. I'm going to have a torque from the weight of that horizontal beam. I'm going to have a torque from my cord that's acting to support all this mess. And I'm going to have a torque from my cord that's acting to support the weight of my sign. Okay. And now I have to think about whether those torques are going to be clockwise torques or counterclockwise torques. Okay. The weight force is going to tend to pull this entire thing kind of in the clockwise direction. So this is going to tend to pull this thing in the clockwise direction. My second cord is going to tend to pull this thing in the clockwise direction. On the other hand, my T1 is going to tend to pull this thing in the counterclockwise direction. We assign clockwise torques to be negative and counterclockwise torques to be positive. Okay, so we will end up with the equation that looks like negative TW plus, what I'm going to say is torque, negative tau W plus tau T1 minus tau T2 is equal to 0. Okay. So let's fill in things now. We know that that in general the equation for torque due to a single force is RF sine theta. Okay. That's a mess. RF sine theta. Okay. So we are going to fill this in on each of these different torques. All right. I'm going to clear the screen, and the nice thing about videos is we can always pause them and go back to them. But I'm going to clear the screen. There we go. And now I'm going to start filling in those torques. So for the first one, we had the torque due to the weight of the beam. So I'm going to have negative RW times the weight of the beam times sine of theta sub W. That's the sine of the angle between R and W. And then I'm going to have a plus R for T1 times T1 times the sine of the angle between T1 and my beam. Okay, that's a 30-degree angle. We can see that in the picture. And then minus R T2 times T2 times sine of theta T2. And this has all got to sum to 0. Let's fill in the things we know. We know that, well, my weight is going to be right at the center of mass. That's 0.5 meters. Let's see if I can do a little bit better than that with my fancy the stylus that I'm using here. It's my finger. Okay. So negative 0.5 meters times the weight of this horizontal beam. That's 198 newtons. Times the sine of the angle between that 0.5 meters and that 198 newtons. That looks like a 90-degree angle to me. Okay. Moving onwards, that cord is attached 0.5 meters away from the wall. The tension in that cord can have a maximum value of 920 newtons. And then the angle between that cord and our horizontal beam is 30 degrees. And then lastly here, it's amazing how quickly I run out of space. I've got the place where the actual sign is hanging from at the end of the beam. That's 1 meter from the wall. Times T2, that's the actual tension in that cord that the sign is suspended from, times the sine of 90 degrees. Okay. All right. So if I figure out what all of these different values are here, I end up with negative 99 Newton dot meters due to the torque of the weight of that horizontal beam. I end up with a positive 329 Newton dot meters due to the torque from the suspending rope there. And then lastly, I've got negative 1 meters times T2, and this all totals to 0. So let's see, putting this all together, I end up with 230 newtons dot meters is equal to, well, 1 meter times T2. So I sum those two numbers and I move the 1 meter times T2 over to the right-hand side by adding that term to both sides. If I divide both sides now by 1 meter, I end up with, well, the maximum size of the force that T2 can have is 230 newtons. And let's think about what that means then. If that cord that's suspending my sign can have a maximum force of 230 newtons before the first cord snaps, that means that the weight of the sign can be at maximum 230 newtons. Let's see, if I wanted to know, that sign's highest possible mass, I could divide that weight by 9.8 meters per second squared by the value for G. And that would tell me that the maximum size mass of my sign is something like 23 kilograms or so. All right. So that answers the question that I have on the screen. The question that I have on the screen asks for the maximum weight that sign right there could be. And we figured out that the maximum tension in that cord is going to be 230 newtons before that cord snaps. Well, if the maximum tension in that cord, the first cord, the cord suspending the sign is 230 newtons, then the highest weight the sign can have is 230 newtons. I can divide that weight by 9.8 to get the sign's mass, which would be 23 kilograms, which is a pretty high-sized mass, honestly, for a sign. let's see here. What else could we do? Well, I'm kind of curious about what's going on at the axis there at the wall. So maybe let's take a look at that real quick. I've got T2 is 230 newtons, and uh, so I figured that out. Let's see what we can do from here. First off, let's redraw that extended free body diagram. So I had something like that. Then I had T1 this way. I had weight this way. T2 T2, whoops, wrong way. Sometimes it's hard being me. I'll tell you what, let's start over. I think that'd be the wiser choice here. There we go. There's that. There's T1. There's the weight of the sine. There's T2. We said that we have horizontal and vertical components. Okay. So I'm a little curious about that vertical component right there. I'm going to focus in on that. Well, let's see. I know that in order for this sign to be in equilibrium, that the sum of the forces has got to be zero. This is true in both the X and Y directions. I want to focus in on the Y direction for the rest of our discussion. So what I can do is I can take this T1 force here, and I can break it up into its X and Y components. Let's do that real quickly. T1, T1X, T1Y. That angle right there is a 31, or excuse me, is a 30-degree angle. We have that in the picture. So as a result, if I think about my SOHCAHTOA, my opposite adjacent hypotenuse, I can use sine to figure out that side that's opposite that 30-degree angle. So T1y is going to be equal to T1 times the sine of 30 degrees. And now we said that, well, we know that T1 has a maximum value of 920 newtons if we hang the maximum size mass off of that second chord, and that's going to give us that T1y is equal to let's see, 460 newtons. All right, so that's T1y. Awesome. Let's think about what's going on here with our sum of forces in the y direction. Well, we've got T1y acting upwards. We apparently have that V acting upwards. We've got the weight of that horizontal beam downwards, and then we've got T2 downwards. Okay. So that's what we have there. Now, let's see what happens when I fill in numbers. I'm going to hold on to that 460 for right now. T1y, we said, is 460 newtons. Okay. And then I've got plus V minus the weight of the beam itself, which is 198 newtons, minus T2, which we just figured out was 230 newtons. So if I total all this, I get V, let's see, 460 there, minus 198, minus 230. I end up with V plus 32 newtons equals 0. Let's see, 460 minus 198 minus 230. Yeah, it gives me V plus 32 newtons is equal to 0, which means that if I solve for V here, V is going to be equal to negative 32 newtons. Well, what the heck? What does that mean? That means that I actually got the direction of this thing, the direction of my vector wrong. Instead of having it upwards, It actually should have been downwards, but that's okay. It still worked out for our analysis. It's just that when we did the analysis, we got a negative number, which just meant that we got the direction of the arrow flipped. It should have been directed downwards instead, which is kind of interesting to think about, but I guess that's the way things work out for this particular problem. I kind of knew that from the beginning, and I could share more about that. If you're interested, you can, contact me and ask me, and I'll be happy to discuss it further. That is going to do it for this. As soon as I find the stop button.